Did we get Earth's water story completely wrong? For decades, we thought our blue planet started dry, only getting its oceans from space rocks. But what if the water was here all along? You know Earth, right? That beautiful blue marble hanging in space covered in vast oceans. About 70% of the surface is water. It's the defining feature, the cradle of life. We've always wondered where it came from. The story we were told goes like this. Young Earth, born super close to the sun, about 150 million kilometers away, was a scorching, dry wasteland. Too hot for water ice. Any water it might have had would have been vaporized by collisions, especially the giant whack that formed our moon around 4.5 billion years ago. So the oceans must have arrived later, a special delivery service courtesy of icy asteroids and maybe some comets, pelting the cooling planet over millions of years. This became the standard textbook explanation, the Late Veneer hypothesis. Makes sense, right? A dry beginning, then a cosmic watering can. But hold on, recent science, like really recent, is throwing a massive wrench in that story. A team at the University of Oxford, publishing their findings just this year, took a closer look at some very special meteorites. And what they found suggests Earth wasn't born dry at all. It might have been born with the ingredients for water baked right in. So how did the old story stick for so long? Well, it had some pretty good evidence. First, the heat argument. The inner solar system was hot. Second, the giant impact argument. That would have definitely boiled off any surface water. Third, and this was the big one, chemical fingerprints. Scientists looked at something called the deuterium to hydrogen ratio, or D/H ratio. Think of it like a chemical accent. Deuterium is just heavy hydrogen. Water formed in different places in the solar system has different amounts of this heavy hydrogen, giving it a unique accent. When they measured the D/H ratio of Earth's oceans, it didn't match the primordial gas of the solar system, and it didn't really match most comets either. Their water often had too much deuterium, the accent was too strong. But bingo, certain asteroids, specifically carbonaceous chondrites from the outer asteroid belt, had water locked in their minerals with a D/H ratio that was a near-perfect match for Earth's oceans. Case closed, right? Earth formed dry from inner solar system stuff, then got watered by outer solar system asteroids. But here's the twist. There's another type of meteorite, much rarer, called an enstatite chondrite, or e-chondrite. These guys are weird. They formed under really oxygen-poor conditions, super close to the sun, maybe even inside Mercury's orbit. They're chemically very strange, full of minerals you don't see often. Why do we care? Because across a whole range of other elements, oxygen, titanium, nitrogen, and more, these e-chondrites are an incredibly close isotopic match to Earth's mantle rocks, closer than any other meteorite type. This strongly suggests that stuff like e-chondrites, not C-chondrites, were the primary building blocks of Earth. See the problem? Earth's main building blocks seem to be these e-chondrites, which everyone assumed were bone dry because they form so close to the sun. But Earth's water looked like it came from C-chondrites from far away. It was a puzzle. Earth built from supposedly dry bricks, then water delivered separately. It worked, but maybe it wasn't the whole story. Scientists kind of glossed over it, focusing on that compelling D/H water match with the C-chondrites. After all, E-chondrites are rare. Maybe they weren't representative. To find these rare messengers, scientists go to extreme lengths. Think Antarctica. Teams camp out on the ice for weeks in freezing temperatures, scanning the vast white plains for dark rocks fallen from space. Programs like ANSMET, the Antarctic Search for Meteorites, have recovered thousands of samples preserved in the ice. And one of those samples, a fist-sized e-chondrite called Larkman Nunatak 12252, or LAR 12252, became the star of the new Oxford study. Now, the idea that e-chondrites might not be totally dry wasn't completely out of the blue. Back in 2020, a French-led team reported that e-chondrites actually contained a surprising amount of hydrogen, potentially enough to fill Earth's oceans 3 times over. And their bulk hydrogen and nitrogen isotopes matched Earth's mantle. But they couldn't pinpoint exactly where most of that hydrogen was hiding, leaving skeptics wondering if it was just contamination from Earth, maybe from the Antarctic ice itself. This is where the Oxford team came in. Using a powerful X-ray technique at a synchrotron facility, think super-powered microscope, they zoomed in on the structure of LAR 12252. They suspected sulfur might be involved, given how much is in these meteorites. Initially, they looked where the French team had found some hydrogen, but then, almost by accident, they scanned the matrix, the fine dust gluing the meteorites' larger grains together. And boom, they found it. The matrix was packed with hydrogen, chemically bonded to sulfur, likely as hydrogen sulfide, H2S, tucked inside an iron sulfide mineral called pyrrhotite. This hidden stash accounted for most of the hydrogen, way more than found elsewhere in the meteorite. Crucially, they showed this wasn't contamination. Areas of the meteorite with visible weathering, like rust or cracks from its time on Earth, had almost no hydrogen sulfide. The signal was strongest in the pristine, unweathered matrix. It looks like this hydrogen was native, part of the meteorite from the very beginning, 4.56 billion years ago. So what does this mean? It means the building blocks of Earth, the chondrite-like materials formed near the sun, weren't dry. They were actually hydrogen-rich, not necessarily carrying water ice, which wouldn't survive the heat, but carrying hydrogen locked chemically into minerals. Earth didn't need a late delivery of water from afar. It seems it accreted the ingredients for water right from the start: hydrogen from sulfides and oxygen from the silicate rocks. The water itself could then form later, as the planet differentiated and cooled through chemical reactions inside the Earth. It wasn't born wet, perhaps, but born hydrogen-rich, ready to make its own water. This discovery really shakes the foundations of the old Late Veneer story. If Earth building blocks had plenty of hydrogen, the main reason for needing that late delivery just evaporates. Making oceans becomes less about a lucky cosmic coincidence and more about a natural consequence of planet formation using local materials. It's a simpler picture, potentially. Earth built mostly from one type of stuff that provided both rock and hydrogen. Now, science is rarely black and white. This doesn't mean the late impacts didn't happen, or didn't deliver any water or other important elements like carbon or those iron-loving metals found in the mantle. They probably did contribute something, but maybe they just topped up the tank or delivered specific flavors of elements, rather than providing the bulk of the oceans. The story might be a mix, mostly homegrown water with a splash of imported stuff. There's still work to do. A key piece missing is measuring the chemical accent, the D/H ratio, of that specific hydrogen sulfide found in the meteorite matrix. If that matches Earth's water, it would be incredibly strong evidence. Until then, some skepticism remains, especially about ruling out all contamination over the meteorite's long stay in Antarctic ice. But the evidence is mounting. The implications here are huge, stretching far beyond Earth. If rocky planets forming close to their stars can naturally trap hydrogen in their building blocks, then water-rich worlds might be much more common than we thought. We wouldn't need that special delivery from the outer solar system every time. Habitable planets with oceans like ours might just be a standard outcome of planet formation in many systems. Think about Mars. Evidence suggests it had water early on. Maybe it too formed with intrinsic hydrogen. This boosts the odds, maybe significantly, that we're not alone, that other Earth-like planets with water and maybe life are out there. It reframes Earth not as a lucky fluke, but potentially as a typical example of a wet, rocky world. This also forces us to rethink models of how planets form and what their early atmospheres might look like. Maybe early Earth, outgassing hydrogen sulfide along with water vapor, had a very different primordial soup than we imagine. So the story of Earth's water is getting a major rewrite. What we thought was an external gift now looks like it might have been an inside job. It's a testament to scientific detective work, teasing out secrets from tiny grains inside a 4.5 billion-year-old rock found on the most remote continent on Earth. It connects the microscopic world of mineral chemistry to the grand scale of ocean formation and the potential for life across the galaxy. It leaves us wondering, if Earth made its own water from the start, What else did it have baked in? What other secrets about our origins and our place in the universe are still locked away, waiting to be discovered in these messengers from the dawn of the solar system? Makes you think, doesn't it? What else did we get wrong? Keep asking questions. Keep exploring. You might just find the answers hidden in plain sight. Stick around for more deep dives into the universe's biggest mysteries right here on Deep Research.